Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture of the fifth module, which is sliding contact bearings. In the first lecture, we studied about the introductory part of the bearings, the two different type of bearings which are generally in use, the sliding contact bearings, rolling element bearing. Then we studied in the case of sliding bearing, different nomenclatures and the principle of development of hydrodynamic pressure. So, in that we studied the two plates. One plate was assumed as parallel plates and the bottom plate was fixed and the upper plate was moving with a surface speed equal to capital U, and in the second case was the case in which there were again two parallel plates, but the bottom plate was fixed and the upper plate was moving in the vertical direction. The two types of flows which we obtained in this way was used to get the flow of the fluid when there was a case in which the bottom plate was fixed and the top plate was inclined and moving with a speed U in the horizontal direction, and it was found that in the third case the velocity profile of liquid will be summation of the first two cases, and with that a hydrodynamic pressure was developing. So, the basic thing was the hydrodynamic pressure develops when a fluid is forced to move from a bigger cross sectional area to a smaller cross sectional area, or the flow is through a vase shaped plates. The same principle now we are going to show for the case of a hydrodynamic bearing. Let we have a hydrodynamic bearing given by this dashed line is the inner surface of the bearing shown by this red colored circle, and the shaft is this one, this is the shaft shown in green color. So, initially when the shaft is stationary, that means the shaft is not rotating, then the shaft will rest at the bottom part of the bearing, okay, and so the red colored circle and the green colored circle are touching at this point, the bottom point. So, initially the shaft is at rest, which is shown in this figure, and it sinks to the bottom of the clearance space under the action of load W. This load W, the radial load W is acting on the shaft, and that radial load may be due to the power which is to be transmitted with the help of any machine elements such as the gears or the belt and rope drive or chain and sprocket, anything. So, due to transmission of load on this shaft, a radial load W is acting. You may say 2 times W, and so on both the bearing the radial load is equal to W and W. That will be the reaction in this way. Okay. So, the radial load acting on the shaft is W, and due to this load W, initially the shaft will be resting at the bottom of the bearing. Now, at this stage, the center of the bearing is shown by this O, and center of the shaft is shown by this O dash, and the O dash is the distance of the two centers. This. The surfaces of the journal and bearing touch during the rest. As the journal starts to rotate, the journal is starting to rotate, the one thing which should be clear here, that the part of the shaft which is inside the bearing is called the journal. Okay, so this length of the shaft will be journal. Like you have a shaft here, and this part of the shaft is inside the bearing. The length of the bearing is L. Let is L. So this part of the shaft is called journal. Okay, so once the shaft start rotating, then surface, and it will climb on the bearing on this way. Okay, due to this rotation, it will climb on it. You may see it like this. The journal will be at this location. Due to further rotation, it may come to a point touching here. So it is just rolling on the bearing surface, on this bearing surface, as you are giving rotary motion to the journal or the shaft. So as the journal starts rotating, it climbs on the surface of the bearing. Okay, and so the center of the journal will move like this way, and due to this movement along the clearance space, a wedge shape is creating. This wedge shape you may see in the clearance space, which is shown in the as a dotted points. This is the clearance space where lubricant is filled. Lubricant is there, and if you see with the climbing of the journal, the clearance space is divided into two parts. The first is, and that part you may see by joining the center of the bearing and center of the journal, O dash, and joining it. So this line of center is dividing the clearance space into two parts. In the first part, the fluid is moving, the movement of fluid is in this way, in the clearance space, just similar to the movement of the journal. So in the first part, which is shown by this yellow color, this is the first part. In the first part, fluid is moving from a smaller cross section to the bigger cross section, converging diverging zone. And in the second zone of the clearance space, that space is shown here. this part of the clearance space where fluid is forced to move from bigger cross sectional area to a smaller cross sectional area is just analogous to the flow of fluid between the inclined plane, like this. Here the fluid is moving from bigger cross sectional area to the smaller cross sectional area, and we studied in our lecture 1 due to movement of fluid under this wedge shaped area, pressure develops. So in this case also, as the fluid is moving in this way, so the similarity is there. Similarity means the bearing surface, this one is stationary, and so it may be this plate, and the journal surface is moving, so that may be this surface, and this surface is moving with a surface speed u. Okay. So due to this movement, a small pressure will develop here, and this pressure will shift the journal from this 4th quadrant to the 3rd quadrant. Okay. And that is shown in figure number C. In this figure number C, now the journal center, which was earlier in quadrant 4th, is now shifted to quadrant 3, and the speed has also increased. So with this increase of the speed, now the diverging converging area, similar to this one along the line of centers, now the line of center is this one. This is line of centers. So line of center divides the clearance space into 2 zones, the converging diverging zone and the diverging converging zone. So this is the zone where the flow of the fluid is from bigger cross sectional area to the smaller cross sectional area, this zone, and it is analogous to this one, and so a pressure will develop, and that pressure will be something like this here. This pressure will lift the journal, and there will be liquid between the journal and the bearing, and this journal is rotating in a clockwise direction. Now if this journal would have rotating in the anti-clockwise direction, then the equilibrium location will not be in the 3rd quadrant but in the 4th quadrant. That means if the rotation of the journal is in anti-clockwise direction, that means it is rotating in this way, then equilibrium location of the journal center O dash will be somewhere here and O will be here. And you may say this O as a center of the bearing, OB, and center of the journal as OJ, and this OB OJ will be the eccentricity by which the journal is eccentric to the bearing center. So since more and more fluid is forced into the wedge shaped clearance area, this wedge shaped clearance area, pressure is generated within the system, and that is very much similar to the analysis which we did in our previous class. That means when we have a plate which moves in this way, is a fixed, then the pressure profile is velocity profile is something like this, with this as a u, this as a u. And when a plate is moving in this way, then the flow of liquid will be from this to this, and due to that the velocity profile is this and this way, and when the plate is moving in an inclined way, the wedge shaped, so in that way the velocity profile at this end and velocity profile at this end, at the entrance and exit, will be summation of these two. And in this type of flow there will be a pressure gradient. Here you will have a maximum pressure, here the minimum pressure, and due to this pressure gradient flow is taking place from this place to this place, and similarly here is the maximum pressure and at this location will be the minimum pressure, and due to that the flow will be in this direction. So if a plate is moving downward, then a pressure develops. Now as this situation is summation of this first and two, and so when the inclined plate is moving, a pressure is developed in this. The similar thing is occurring here. Here a fluid is forced to move from bigger to smaller cross section, the wedge shaped flow is there, and due to that this pressure is developing. There is a pressure profile like this. Okay. There will be a maximum pressure, and there will be location where the pressure will be 0 and 0. Now since the pressure is created within the system due to rotation of shaft, this type of bearing is known as self-acting bearing, because you are not supplying any pressurized fluid. The journal is rotating, and due to rotation of the journal automatically a pressure is developing. The pressure generated in the clearance space supports the external load W. Here again the journal and the bearing is shown, and in between is the clearance. This clearance space is highly exaggerated, this much of clearance will not be there, the clearance is very, very small. Okay. Here the lubricant flow is shown, this is the rotating shaft, this is the lubricant, this is the fixed bearing, and the external load is acting along the center of the journal OJ, and this is center of the bearing OB. And the pressure has developed like this. Here a partial bearing is shown. Okay. The oil of viscosity mu and flow rate Q is supplied, and the load W is there. The difference between this OB and OJ, is eccentricity E, and if the journal centers are joined, OB and OB is joined and extended, then at a particular location along this you get a minimum film thickness. This is the minimum film thickness. Okay, this one, and this is called the HO, which is the minimum film thickness. Well, and that is shown here also. This one is the minimum film thickness along the line of centers. Now, some important dimensionless parameters which are used in the analysis of sliding contact bearing are, first, the R by C. R is the radius of the journal and C is the radial clearance. Radial clearance means you have a bearing, inner surface of the bearing, and let the shaft is eccentric, shaft is centric with the bearing center, then this is the journal, okay, and both centers are same, OB and OJ are same, concentric. Then the diameter of the shaft is D and the diameter of the bearing is let capital D. Inner surface, inner diameter of the bearing is capital D. So, capital D minus small d divided by 2 is this clearance, and that is along the radial direction, and so it is called the radial clearance. Okay. So, this is called the C. Then R divided by C is called the radial clearance ratio and it is a non-dimensional parameter. Another is mu n by p, and we have seen this parameter while we derived the Petrov's equation. The Petrov's equation was giving the coefficient of friction F as a proportional to this mu n by p, and it is also proportional to R by C, two non-dimensional parameters. This mu n by p is called the bearing number, and in this bearing number the terms are mu is the dynamic viscosity, n is the rotational speed of the journal, and p is the unit load, and we had derived this unit load as this unit load is equal to the radial load which is acting on the journal. So, on this journal the radial load acting is W divided by the projected area which is supporting this W, and the projected area which is supporting is equal to diameter of the shaft multiplied by length of the bearing. So, you may see that this is your journal and the bearing is having length L. This is the length of the bearing L. Well, the diameter of the shaft is D, and the radial load which is acting on the journal is W. So, the projected area which is supporting it is equal to L multiplied by D. So, W divided by the projected area which is supporting it is given by the unit load capital P. So, this mu n by p is a dimensionless parameter. Later on from the Petrov's equation, we found another parameter, dimensionless number, which is called the bearing characteristic number or the Sommerfeld number, and that is given by this S alphabet, and it is equal to R by C square. This will be non-dimensional parameter because R will be in mm and C will also be in mm, multiplied by mu n by p, the bearing number which was taken in the Petrov's equation. Now, the interesting relation is F, that means coefficient of friction, and R by C, the radial clearance ratio, is given by 2 pi square mu n divided by P R by C square, and that is 2 pi square multiplied by Sommerfeld number. It means this parameter F is the coefficient of friction, it is non-dimensional parameter, and R by C is also non-dimensional parameter. So, this complete term is a non-dimensional number, and this is proportional to the Sommerfeld number. So, knowing the Sommerfeld number, you can find this parameter, and from this parameter, knowing the value of R, the radius of the journal and the clearance between the journal and the bearing, you can get the coefficient of friction, or the friction which is acting between the shaft and the bearing, and this friction will be responsible for heating the lubricant and power loss also. Now, let us study the stability of a hydrodynamic bearing system when it will be stable. The Mackey's brothers conducted an experiment, and based on that experiment they drawn this figure, in which along the x axis was bearing characteristic number mu n by P, and along the y axis is the coefficient of friction F, and the curve is given by this B, C, and then C to D. Now, this curve gives us the basic information about the stability of the journal and the region in which the journal can be run safely. So, as seen in the figure, there are two distinct parts of the curve, the B, C, thereafter the minimum coefficient of friction is there, and then again from C to B, with the increase in bearing characteristic number, the coefficient of friction is increasing. In the region BC, there is partial metal to metal contact and partial patches of lubrication, and so this region is called the thin film lubrication or thin film area, where the lubricant, this surface is something like this, one of the surface, another is this way. There is very thin film between the two surfaces. This is the condition of thin film or boundary lubrication. In the region CD, there is relatively thick film of lubricant and hydrodynamic lubrication takes place. In this zone, the surfaces will be something like this. Two surfaces, in between there is a lubricant, and the surfaces are sufficiently separated from each other, and so there is a full film lubrication, okay, or thick film lubrication, thick film. AC is the dividing line between these two modes of lubrication. The region of the left of the line AC is the thin film zone, while the region to the right of the line AC is the thick film zone. It is observed that the coefficient of friction is minimum at C or at the transition between these two curves. The value of the bearing characteristic number corresponding to this minimum coefficient is called the bearing modulus. This is denoted by K in the figure. Now, the guidance for the stability, or why we are saying the zone left to the line AC as a thin film or the unstable zone, and the zone to the right as a stable zone. That you can find by selecting any operating point. Operating point means the operating point will be decided by this mu n by p. Mu means which lubricant you have taken in the clearance space. You have a bearing like this, and the journal is rotating in a clockwise direction, and so its equilibrium location is its center of location is OJ, O journal, and this is OB, okay, and joining these two is the line of centers, and your journal will be something like this. This is your journal. So you have taken some lubricant, and that lubricant is filled inside this space. Okay. This lubricant has viscosity given by mu, and your journal is rotating with a speed given by n, and on the journal the load which is acting, the radial load which is acting is W. W, radial load is acting on the journal. Now you have some radius of the shaft. By design of the shaft, you have selected a radius of the shaft, and you have a bearing, and this bearing has length given by L. So from this R, L and N, the operating parameters, you will get the bearing characteristic number, and that is mu n divided by P. So from the operating parameters, you have the mu n divided by P. So let the parameter which you have selected is landing you somewhere here. The parameters which you have selected is landing you somewhere here. Your bearing characteristic number is in this zone, left to the line AC. Then corresponding to this, the coefficient of friction will be given by, let me draw a straight line. The coefficient of friction will be given by this. This is the coefficient of friction. Now we want that whether the bearing which is operating here is stable or not. The meaning of stable means stability is of three types. When you have this type of case, that you have a ball here on this surface, you have a ball, and its center is somewhere here. Now let due to certain reason or due to certain disturbance, this ball is shifted from its equilibrium position to this location. It is disturbed. It is displaced from its equilibrium location. So what will happen? Due to gravity, it will come down. Again, it will move up, and due to friction, this amplitude will decrease. Now it will not again come to this location, it will come to a location below the earlier one, and after few vibration or due to or oscillation, finally the ball will come to its original location. So, if this type of case is, that means due to certain disturbance, the equilibrium location is disturbed, but after few vibration or after some time it comes to the original equilibrium position, then it is the stable system. This system is a stable system. Now, if you have this type of surface, flat, and a ball is there, this is its equilibrium position. Now, due to certain disturbance, its equilibrium position shifts to this location. Now, there is no any correction which will bring this ball to its original equilibrium location. It will remain at its new location. This is called the neutral equilibrium. But if your surface is, let something of this type, and your ball is here, and equilibrium position is somewhere here. Now, due to certain disturbance, it moves from its equilibrium location and came to this location. Now, what will happen in this case? What will happen? This ball will continue to go away from its original equilibrium position. It will continue to move away from it, and this condition is called the unstable condition. The system is unstable. Now, let us see, if your bearing is operating left to the AC, then which type of condition is. So, let me erase this so that we may have sufficient space. Okay. So, this was the equilibrium position. Now, let due to any change in parameter, the parameters are mu, n and p, any parameter is changed. Any parameter is changed means, let the viscosity has changed due to increase in temperature of the lubricant, or RPM has changed due to certain variation, the RPM of the shaft has changed, or load has changed. Due to any reason, this mu n by p has changed, and due to this change, the system will now operate at its new location. Now, let that new location is somewhere here. Corresponding to this new location, the friction, coefficient of friction will be this one. Coefficient of friction is reduced. Here the coefficient of friction was more at the original equilibrium position. At new equilibrium position, the coefficient of friction is reduced. Now, with the reduction in coefficient of friction, what happens is the viscosity changes, viscosity of the liquid changes, and it becomes more viscous. We know that with the increase in temperature, the viscosity of the lubricants decreases, and with decrease in temperature, the viscosity of the lubricant increases. It becomes more viscous. So, with the change in equilibrium location, the coefficient of friction is decreasing, and with the decrease in coefficient of friction, what will happen is the temperature will reduce. Okay. With the this coefficient, what this coefficient of friction is doing? It is generating heat, and due to generation of heat, the temperature of the lubricant increases. Now, in this case, the coefficient of friction is decreasing. So, with decrease in coefficient of friction, the temperature will decrease, and with decrease in temperature, the viscosity will increase. Now, with the increase in viscosity, now what will happen? this mu n by p, this mu n by p will further increase because mu is increasing. So, it will further try to move in this direction away from the equilibrium position. So, which condition is prevailing? This one, where the ball was at the top of this surface, and when it was displaced, it was going away from its equilibrium position. It was not coming back to its equilibrium position. So, the same is visible here. Now, you may see on another case where there is a decrease in bearing characteristic number. This was the original condition, and due to any change in parameter, now the equilibrium position has shifted somewhere here. Now, with this what will happen? Let us see. The coefficient of friction is increasing. It is now increasing. Coefficient of friction is increasing. So, with increase in coefficient of friction, more sliding work will be done. The temperature of the lubricant will increase, and with increase in temperature, the viscosity will decrease. The meaning is this mu n by p is further decreasing. It means you are moving in this direction. You are not coming back to the original equilibrium position, and that will happen if you are in the BC zone, this zone. Now, let inquire, if you are operating at this zone in CD, then what will happen? Let the operating condition is such that, or the operating parameters are such that your bearing characteristic number is somewhere here, and at this point the coefficient of friction is given by this one, and corresponding to this coefficient of friction there is a temperature of the lubricant, and corresponding to that temperature there is a fixed value of mu, and that is given by this mu, and the parameter is mu n divided by p. Now, let due to change in RPM or change in any other parameter mu or p, the new operating parameter is achieved, and that is somewhere here. You have shifted to somewhere here, just like your ball has shifted. You have shifted somewhere here due to disturbance, and now at this point the coefficient of friction is given by this yellow colored, green colored F. Earlier the F was red colored. So, the coefficient of friction has increased. So, with increase in coefficient of friction, with increase in coefficient of friction F, the temperature of the lubricant will increase. The temperature of the lubricant will increase, Now, with increase in temperature, what will happen? The viscosity will decrease. Now, with the decrease in viscosity, what will happen? The new value of mu n by p which is there, now mu is decreasing, and so this parameter will try to come in this direction automatically there is self correction. And so this is a case of this one, where the ball was trying to come back to its equilibrium location. And so this zone is called the stable zone. If due to certain reason this bearing center has displaced to a new location, then there will be automatic correction, and that automatic correction will again bring back the journal center to its original equilibrium location. And the same thing will happen if your parameter will change from this red colored space to a new space given by this blue one. In that case, what will happen? The F is decreasing. F is decreasing. So, with decrease in F, the less sliding work will be done, the temperature of the lubricant will decrease, and with decrease in temperature of the lubricant, viscosity will increase. And so, whatever value of mu n by P is here, with the viscosity will try to increase, viscosity of the lubricant will increase. Increase means this value will increase and it will try to come back to its original equilibrium position. And so, this CD zone is called the stable zone. And this C is the threshold value, and that is given by this K. Okay. So, the threshold value of bearing characteristic number will be determined by this K, and you will try to have a bearing characteristic number more than this K. So, that we will get from the guidelines for stability. In order to avoid seizure, the operating value of the bearing characteristic number mu n by P should be at least 5 to 6 times that when the coefficient of friction is minimum. Okay. 5K to 6K or 5 to 6 times the bearing modulus. If the bearing is subjected to fluctuating loads or impact conditions, the operating value of the bearing characteristic number mu n by P should be at least 15 times that when the coefficient of friction is minimum, 15K or 15 times the bearing modulus. This is the Trumpeter's criteria. This gives us this mu n by P in Pascal second. Pascal second is the unit of mu multiplied by unit of this rotational speed of the journal, and that is revolution per second, divided by this unit bearing load, and that is Pascal, because unit bearing load P is given by W divided by LD. W is in Newton and L and D both are in mm and mm or meter and meter. So, if it is meter and meter, so P will, the unit of P will be Newton per meter square, and that will be the Pascal. This mu n by P should be greater than or equal to 0.362 into 10 to the power minus 6. This is another guideline for stability. We try to find the pressure which will develop in the clearance space, pressure mathematically. So, we will take a journal with diameter equal to small d and the eccentricity ratio equal to the eccentricity ratio given by here epsilon, and clearance equal to C, and eccentricity equal to E, and minimum film thickness HO. The system is shown here, the hydrodynamic bearing system is shown here. The colored part is showing the lubricant, and this journal is rotating in a clockwise direction, and so the fluid in the clearance space is also moving in a clockwise direction. Okay. For the mathematical analysis, we have to take certain assumptions which are called the simplifying assumptions, and the Reynolds was the person who derived the mathematical equation for the pressure which develops in the clearance space in a hydrodynamic bearing system. So, one of the important simplifying assumptions resulted from Reynolds' realization that the fluid films were so thin in comparison with the bearing radius that the curvature could be neglected. Okay, this curvature can be neglected, and so this can be modeled with help of a planar bearing like this. The bearing can be assumed as a plate like this, and the journal can be assumed as a inclined plate. So, this can be, this wedge shaped can be modeled by this one, where this is the bearing surface and this is the journal surface, and journal rotating with sliding velocity u, capital U. So, this is your U. This enables the neglecting the curvature, this enables Reynolds to replace the curved partial bearing with a flat bearing called a plane slider bearing. Now, other assumptions which were made in the mathematical modeling were the lubricant obeys Newton's viscous effect. The meaning is the fluid which is inside the clearance space is the Newtonian fluid. Newtonian fluid. And so, it will follow the Newton's law of viscosity. That means, the tau is equal to mu du over dy. Like this, the plate is moving in this way with the speed u, this is a fixed plate, there is a lubricant, and so this type of velocity profile is there. Well, and the velocity gradient is given by du over dy. So, your lubricant is obeying this law. The forces due to inertia of the lubricant are neglected. That means, your F is equal to ma, this acceleration effect is neglected. The lubricant is assumed to be incompressible. The viscosity is assumed to be constant throughout the oil film. There is perfect adhesion between lubricant and bearing surfaces. That means whatever velocity of fluid is in the vicinity of surfaces is the velocity of the surfaces. It means if the surface is stationary, then the fluid which is touching this surface will have 0 velocity. And if this plate is moving with speed u, then the fluid which is just in contact with this plate will have sliding velocity equal to capital U. Okay. The meaning of the fifth assumption is that. Now, using Reynolds' assumption that curvature can be neglected, we fix a right hand XYZ reference system to the stationary bearing. We now make the following additional assumptions. The radial clearance is so small that the pressure gradient across the clearance is neglected. The meaning is this is your bearing and the journal is somewhere here. Now, the clearance space which is shown here is highly exaggerated. This clearance space is very small. So, whatever coordinate system is attached, the variation of pressure along this clearance space is considered as negligible, because this is very small. Thus, the pressure is independent in the y coordinate, because y coordinate was taken along the thickness of the fluid film. You may see here, here the y coordinate is attached along the thickness. Okay. The velocity of any particle of lubricant in the film depends only on the coordinates x, y. This is another assumption. Now, with this assumption, we have taken a bearing shown as a hashed part, and the center of the bearing is this O. Center of the bearing is O, this one, and the center of the shaft is somewhere here. Okay, eccentricity is there, and this is your shaft. Okay, this is your shaft which is rotating with the speed n, and the dotted are the lubricant in the clearance space. Now, we had taken a fluid element, infinitesimally small fluid element, this one, and the coordinate system is along the radial direction is the y-axis, along the circumferential direction is the x-axis. This is your x-axis along the circumferential direction. Along the radial direction is the y-axis, and perpendicular to the screen is the z. Now, this is the side view of the bearing which is shown here, and it is a sectional view. The hashed part is the bearing which is shown here. This is the bearing hashed part, the oil hole is there, and this is the shaft. Okay. And there will be eccentricity between the journal center and the bearing center. And the coordinate system is now, this is the fluid element, and radial direction is y. In this front view, the coordinate system is also shown. This is the z direction. The length of the bearing is L. Okay, this is the length of the bearing, and the thickness of the fluid where you have taken the fluid element is h, and the fluid is moving with speed u at the surface, because the surface velocity of the journal is given by u. So, when you will take the plate something like this, then this plate, which is analogous to the journal, is moving with the u, this u. Well, so now what we will do is, we will take this infinitesimally small element in the coordinate system, in the xy coordinate system and yz coordinate system, and we will see what forces are acting on this infinitesimally small element, and then we will apply the static equilibrium condition. That means summation of forces in the coordinates, different coordinates must be 0, and from that we will get a relationship that will give us the pressure profile in the clearance space of a hydrodynamic bearing. So, we are just stopping the second lecture of this module, which is sliding contact bearing at this stage. In this, the important thing which we studied is the stability of the bearing. What should be the value of mu n by p, which is the bearing characteristic number for stable operation of the bearing. And then we started mathematical modeling of the fluid film bearing to get the pressure profile in the clearance space, which is the hydrodynamic pressure and which lifts the journal. Now, we will continue this mathematical modeling, and we will find a equation which is called the Reynolds equation to get the pressure distribution. After getting the pressure distribution, different other parameters are determined, or by solving that Reynolds equation, we will get the pressure profile, and then other parameters are found. So, thank you.